So thank you for joining Imaging and Inverse Problems, this OneWorld SIAM Imaging Science virtual seminar series. So today we are happy to invite Professor Bao Chenglong from Tsinghua University to give a talk. Professor Bao got his PhD from National University of Singapore at the 2014, and now he is working at the Yale Mathematical Science Center at Tsinghua University. His research areas include mathematical image processing, convex and non-convex optimization method, computational harmonic analysis, and deep learning. And you see in the slide, Professor Bao will give a talk, and the title is Learning Robust Imaging Models Without Paired Data. Okay, thank you, Chenglong.
Thanks, Professor N, and thanks for the invitation and kind introduction. Today, I will introduce my recent works on unpaired data learning in image processing. This is the outline of my talk. I will introduce two cases in unpaired data regime, including the single image case and the dataset case. Let's start with image model. It is clear that it is a highly nonlinear process. Take this quantitative stability mapping imaging as an example. This is the face imaging in MRI. In its figure, the QSM actually contains 4 procedures. The first procedure is the offset correction, and followed by the face unwarping and background field removal. And the last step is we usually do some research in inverse problem community. This is a dipole inversion. Also, although the last step is a linear process, but the whole process in this image process, it is clearly a highly nonlinear process. Usually, we always want to relax this highly nonlinear process to a linear approximation by using some kind of approach, like the Taylor expansions. But if we apply this a first order approximation, this forward operator A is never perfect or sometimes contains errors, which means that our linear equations always contain some error. This is called the delta A. And also, we know the observations contain some complex noises, and the noise distribution delta B is very complex in many practical examples. If we do not take these 2 errors into a full careful considerations, this error may lead to severe artifacts in our recovered image. Let's see 2 examples. The first example is the blind image deblur. In this application, we know that our observed image is a convolution with a blur kernel and a ground truth image, and then corrupted by a Gaussian noise or some noise. And the estimation of this blur kernel plays an important role in this application. Usually, the accurate estimation of this K is very, very challenging, which means that in the forward model, the delta A exists. And in this figure, we know that if the estimated kernel has 2 pixels errors, we will see that the direct deconvolution by using the Richard-Lucy deconvolution method, it causes many running artifacts here. So this is the first example. Let's take the other example is the hyperspectral image denoising. In the hyperspectral image denoising, we can assume that this observation can have some certain kind of low rank approximation plus some noise. And in this case, we know the forward model A is correct, but the noise distribution N is very, very complex and it depends on the frequency band or depends on the context. If we want to find the low rank approximation, the simplest way is to do the singular value decomposition. If we use this method, we implicitly assume that the noise distribution is Gaussian. However, if this results by the SVD decomposition, we will see these line artifacts in the recovered image here. So to address the above issues, traditionally we try to get some more accurate models The first attempt is that we can try to get the description of this delta A by using the underlying image principles, which means that we can transfer this linear equation to another linear equation by get a better A hat. In this case, the A hat may be nonlinear or a new linear equation. So we solve this equation and we hope we can get a better X. Sometimes we know the delta A is very, very complex, and we try to find the pattern of this delta A X on the true image X, which means that we decompose this linear equation to another linear equation by introduce some variable B. And in this linear equation, that contains two errors. This error V is a structural error that depends on our forward operator. And this N is a random noise. So if we can have certain good regularization of this structural error, then we hope that we can decompose this a better reconstructed image X. So this is actually the two-way to get a better accurate model. And to describe the complex noise, and we know there are many works on these directions, then we can use a Laplacian noise or mixture of the exponential power distributions and extra. In summary, in our traditional method, we put our effort to find an accurate forward model. And together with proper numerical algorithms, we hope to get good results that satisfy the application's requirements. So actually, we put our effort in this direction. And the numerical algorithm is not the main goal of today's talk. In recent years, as we know, the deep learning-based methods have shown great success in many tasks. If we have enough training data, we hope we can directly find an end-to-end mapping parameterized by this theta. And if we minimize these loss functions, and we hope that we can directly find a mapping between the noise image and the clean image, no matter this A contains error or not. In deep learning method, it actually consists three components. The first component is we need to construct a network. Usually, this is a handcrafted engineering. Recent works have used a knowledge-injected network. For example, we can unrolling certain kind of optimization algorithm to get a network. Also, inspired by the connections between network and the partial differential equation or ordinary differential equations, we can construct a new neural network. Also, we can put some regularizations as a network module inside the network architecture. So in this case, we hope we can get a better network architectures. Once we get a good network, and we construct a proper loss functions by using like the cost entropy or contrastive loss, and minimize this loss using a proper chosen network training algorithms, we hope we can get a good results. In fact, the choice of the network training algorithm that's induced several the implicit regularizations. So which means that at all these three steps,
Oh, sorry, maybe the network is not stable. I mean, so maybe we need to wait. Chenglong is come back now.
Oh, yeah, I'm sorry.
Maybe the network is stable. It's okay. Yeah, you share your slides again and then start your talk again.
Okay.
No problem.
Okay. When I stop, is from this slide?
Yeah.
Okay.
Exactly. Please.
Okay. In the deep learning method, we actually construct the networks and we minimize this loss function, and we hope we can directly find an end-to-end mapping that we can map a noise image into a clean image. And the deep learning method that consists of three components. One is a network architecture. We can use some basic components like the convolution layer or pooling layer to get a network. Also, recently, we can use some knowledge-injected network. For example, we can unrolling some optimization algorithms or unrolling some numerical algorithms to get a network. Also, we inspired by the connections between network and the partial differential equations, we can get a new network. Also, we can inject some regularizations into the network as a network module. Once we construct the network, we need to design a proper loss functions. For example, in image recognition, we use the cost entropy, or in unsupervised learning, we use contrastive loss. By minimizing this loss function using like the stochastic gradient method or momentum-based method, we can get our network. As a whole, the above three ingredients makes the success of deep learning methods. However, it is well known that training deep neural networks needs a large amount of training samples. This is difficult in many real applications due to the following three reasons. First of all, we hope that we can try to do some simulation. We can do some simulation data and try to learn the network. But the simulation data is not accurate for practical applications because we don't know the degradation process or we don't know the noise distribution, which means that the simulation data has some distribution shift with the real data, which may deteriorate the performance of the networks. Also, we can try to conduct some experiments and we ask some people to do the labeling work. As we know that this require labeling is time consuming and some applications require some domain experts. Also, in the medical imaging or financial data processing, sharing data is very difficult due to the security reasons. As an example, let's see the data collection process in video superresolution. In this process, we use an iPhone and we use two cameras in the iPhone to capture two video sequences. And by using an iterative alignment of this high resolution image and the low resolution images, and we can cropping these two sequences to get our data set. This flow is simple, but when we construct this data set, we have many reasons to be considered. Why is the data set diversity? We need to construct this data by using the outdoor or indoor scenes, or we have the sufficient motion statistics. Also, in the labeling process, we need to do this iterative alignment for each frame between high resolution sequence and the low resolution sequence. It is actually very time consuming. So this is just one example. In contrast, in this talk, we will consider the unpaired data regime. And in this figure, we can see that in the classical paired data, we have some xi and yi. Then I can learn a network that maps the xi to yi. But in the unpaired data regime, we are giving a set of clean image and a set of noise image. But I don't know the correspondence between x and y. In other words, the x is sampled from px and y is sampled from py. And in this setting, how can we construct a deep neural network to do the image processing tasks? First of all, we know in this regime, it significantly reduces the data dependence since we do not require the labeling. And it is also very easy accessible in many applications. For example, in super resolution, we can download many images of different resolutions via internet. Also, in this regime, it is different from the few-shot learning or semi-supervised learning, because in these two learning schemes, we need several pairs data. So the goal of this talk is that giving unpaired data and inaccurate image model. Our goal is to find some suitable mappings that we can find this map between the clean image and noise image. So we want to find this F or G. And in this regime, we have two cases. The first case is that if I only have an input noise image Yj, and for each Yj, I want to find the mapping Gj, such that this Gj maps Yj to a clean image. Also, in the data case, we have another subcases. The first subcase, the case is that we only have a set of noise image, and we hope we can find a mapping that directly finds the clean correspondence of this noise image. Furthermore, if I give a set of unpaired data xi, I want to find both G and AF simultaneously, such that we can generate the clean image or noise image. So let's take a little bit more details of these three cases in this talk. Now let's go to the single image case. Image denoising is actually a classical topic in image processing. Many researchers have put great efforts in Gaussian denoise problem, and currently we have many excellent Gaussian denoiser. For example, BM3D. But in a commercial cameras, this is the process of the ISP unit in this camera. And in this dash box, it contains many different kinds of noise. For example, it contains the fixed pattern noise, shoot noise, or quantization noise. So when we get this JPEG image, we actually have this noise, this image actually contains the composition of all these different kinds of noise. So the composition of this noise makes the practical denoising problem highly non-trivial. And in this case, we know our forward model A is equal to identity, is accurate, but the noise N is complex. So this is an example of two images captured by the smartphone from the SIDD dataset. And we plot the noise distribution in the red, green, and yellow patches. This is the noise distribution in the third column. We will see that the noise distribution is not Gaussian for these real images. And the non-Gaussian noise usually weakens the performance of these Gaussian denoisers. So this is straightforward. So our idea is very simple in this case. We try to find some network F theta. This F theta can map the noise image to a latent image Z. And for this latent image, we assume that this latent image Z is a Gaussian perturbation of the true image X. So in this case, if this assumption holds, then we can directly apply our any existing Gaussian denoiser for this latent image Z, and we can get our clean image. In fact, this idea is not new. Before the appearance of deep learning, we attempt to find this transformation F theta, and we try to find some analytical transformation. As we know that if this noise distribution is Gaussian plus Poisson or Poisson, and we can use the variable stabilization transformations. But for the real world noise image, it may be so complex, and we cannot get this analytical transformation. So that's we want to approximate it using deep networks. To formulate our idea, we started from this classical MAP model, which contains the likelihood and the prior term. And in the complex sensing, we always try to get a better prior term. But today we will focus on this likelihood term. As we know, the noise distribution is very complex. We cannot get the exact representation of this likelihood. However, we can using the tools from the variational inference, such that we can get a approximation of the log likelihood. So which means that if I want to ask, the idea of this variation inference is simple. If we want to estimate this log likelihood, I need to calculate this integral. But if our dimension is high, so the calculation of this integral is difficult. However, I can find some proposal distribution Q such that this distribution is easy to calculate, and we can approximate this log likelihood. So this inequality is from the Jensen's inequality, which means that I get a lower bound of this log likelihood, which is called the elbow. We simply reproduce this elbow in this likelihood. So we get our new model is like this. It's a very simple model. The next step is to obtain the computation of this elbow so as we can try to minimize it and to get the estimation of the true image. By the recent work of the variational autoencoder, if I impose 3 assumptions on this elbow, then we can get the exact representation of this elbow. So the first assumption that's consistent with our basic idea, which means that in the latent space, our latent image Z is actually a Gaussian perturbation of the true image X. So this is very good. And the encoder assumption means that we can encode this noise image into a latent image. And the decoder assumption means that we can try to decode this latent image to a noise image. Under these assumptions, we can get the exact representations of this elbow. We can see that this elbow contains 2 terms plus a constant term. The first term, that means that we try to get some autoencoder structure, which means that we first map the noise image to a latent image plus some Gaussian perturbations. And then we decode this image, we try to reconstruct this noise image. So this is the reconstruction loss. And the second term is that in the latent space, we always assume that GY, this is a latent image, is a Gaussian perturbation of X. So this is a KL loss in latent space. Then we arrive at the objective function like this. We try to minimize this model. With the objective variable consists of the image X and the decoder and the encoder. To minimize this model, we introduced an auxiliary variable P is equal to X, and we apply the ADMM method to solve it. When we apply the ADMM method, in the first step, we fix PK and QK, and we need to optimize X, theta1 and theta2, which means that we want to training our decoder and encoder in the first step. And in the second step, we know it tries to find the proximal mapping of this regularization term. By using the plug and play techniques, we know this proximal term can be replaced by any existing Gaussian denoiser X. Because we assume this is Gaussian. So which means that our method can be composed with any existing Gaussian denoiser. So we call our method as NN plus X. This X is Gaussian denoiser. We can use a non-local mean or BM3D or a pre-trained deep neural networks. Before presenting our results, I have to make a remark on our model. As we train a deep neural networks on a single image, the model may have some trivial solutions. It is common in some self-supervised methods, such as deep image prior. In our objective function E, it does have some trivial solutions, which means that the encoder maps the noise image to a constant image, and the decoder maps the constant image to noise image. In this case, we know the objective function value is equal to 0, which means that this is actually a trivial global minimum. To avoiding this issue in our model, actually we can show that if the decoder is composed with this convolution layer or pooling and upsampling layer, we show that the decoder maps any constant image to a constant image, which means that it cannot map the constant image to a noise image. So this is the first explanation. And in our implementation, we usually set this F is very small. And we can see that in a data set, the average the training loss is around 300, larger than 0. And we test our method in 3 data sets. 2 data sets are natural image like CC and poly-U. And 1 data set is from the microscopic images. And our method is composed with some Gaussian denoiser like this NLM stands for the non-local mean, and BM3D and a pre-trained DNCN model. And we report the PSNR and SSIM in each data set. And we will see that our method that improves this classical method by a large margin, usually more than 2 dB. Compared to some VST plus X method, in which the VST is a variance stabilization transform, our method is still better for these real-world noise images. Okay, this is the qualitative results. And the first column is a pair of noise image and ground truth. And we compare our method with some traditional method and the deep learning method. And we will see that in these 2 zoomed in region, the texture is better. And the homogeneous region shows that we remove almost all the noise. Come back to our intuition. Let's take a look at the noise distribution of latent image, because we want to assume that in latent space, the noise distribution satisfies the Gaussian. So the first column is the original noise distribution. The second column, the third column is the distribution using the VST. And the last 2 columns are using our method. We will see that this encoder network that transform this noise distribution more close to Gaussian distribution, so which validates the effectiveness of our method. Finally, we test our method on real-world noise image provided by Huawei company. Actually, we have tested many images, and here we just give 1 example. In this case, we do not have ground truth, and we compare our method with 3 classical methods and 3 deep learning methods. And this is H is our method. We show that we can remove the noise and while keeping the structure information. Actually, in this work, our idea is very simple. We try to approximate the complex likelihood using a generative model. In fact, we can extend this idea to many other applications in image processing. Let's take a look at the image segmentation. Image segmentation means that we try to partition an image into some meaningful regions. And a classical image model is the Chenglong model. And in Chenglong model, we assume that there are in the foreground and background, they are constant. And plus a regularization. This regularization is the length of the segmentation boundary. After proposal of this model, many variants and many works are proposed to improving these models. So this is an important model in image segmentation. So let's take a probabilistic model for this image segmentation. So which means that we can construct a log likelihood term. Here, the fx, you can see that this is a feature extraction functions. And this is a prior term. This is corresponding to the length of the segmentation boundary. So using the MAP model, we naturally give that this model. And the first term is the likelihood. In the CP model, we know that it basically assumes that in the foreground and the background, it assumes that it does have follows the Gaussian distributions. But we know this assumption does not hold in general. These 4 examples that show the distributions of foreground and background. The blue histogram is the distribution of background, and the orange distribution of the histogram is the distribution of foreground. And we know that the distribution of this omega-1 and omega-2 are non-Gaussian, and sometimes it may have a large overlap. So it is natural to expect that CV model fails in these cases. Similar to the case in image denoising, but in this case, we have to introduce two elbows, which means that the foreground, we introduce one elbow, and the background, we introduce the other elbow. Once we take the notation of this segmentation as a mask, UX, and we can impose the CV model on our latent image. And in the latent image, we assume that if UX equal to 0, this distribution is a Gaussian distribution. And if UX equal to 1, it satisfies another Gaussian distribution. And similarly, we impose encoder and decoder's assumptions as follows. Here we just impose this encoder, the variance contains here, so which makes our probability more complex, but the computation is almost the same. And also using the same way, we can get the computation of this elbow, as we know that the first term is a reconstruction loss, and the second term is a KL loss depends on the segmentation mask, UX. So our final model is the summation of this reconstruction loss and the KL loss plus our segmentation boundary. Because here we use we use UX, use the segmentation mask. So we substitute this segmentation length using the L12 norm. Clearly, this model, we can solve it by the alternative minimization, and we can show the convergence in some cases by the standard KL arguments. To test our model, we test our deep CV method. This method we call the deep CV method. We test our method on the Weismann dataset, which consists of 100 color images. And we compare our method with the classical chain-wise model and a graph cut model, normal cut, and a statistical model, which assumes the likelihood is a mix of Gaussian. And also we compare with a deep image prior model, the double deep DIP model, which is proposed in the CVPR 2019. And from this table, we report the F measure and the mean IOU. And we will see that the proposed deep CV model achieves the best F measure and mean IOU in this data set. This is the qualitative segmentation results. The last column is our method. Clearly, our segmentation results are more meaningful and accurate. Also, in this figure, we show the distributions in latent space. The first column is input image. The second column is the latent image. And the third column is the distributions of foreground and background in the latent space. And we see that it's more close to Gaussian. So the chain-wise model that works in the latent space. So now let's go to the dataset case. Why we need to consider dataset case? The previous method does get satisfactory results, but it has to train a new neural network if the input image is changed. So which means that for any given image, we have to train a new neural network. And this figure here that shows the computation time for each image. Compared to this double DIP model, our method is much faster, but the speed is still unsatisfactory. Because for this given image, we still need around 130 seconds. So it's not acceptable for practical applications. So we are considering to train a neural network on a noisy data set. Once we can train this neural network, we can directly inference the segmentation mask. And this will significantly accelerate the inference speed. But it is noticed that we don't have any labeled information. We are only giving a set of noise image. In this case, we can actually use the previous model, which contains the reconstruction loss and KL loss, and plus the summation of these observation images. But we parameterize the segmentation mask by a network, which means that this network, the input is the noise image and the output is a segmentation. Here, we have to change our regularization. This is because the classical regularization in Chen-West model is not strong enough to regularize the whole data set. Thus, we impose two regularization terms in this work. The first regularization is called the augmentation invariant, which means that if I rotate the input image or flip the input image, the segmentation mask should be rotated or flipped correspondingly. So which means that this error should be small. And the second regularization is we call the conservation of region information, which means that we do not want the inference of this segmentation mask is an empty set. So which means we can train a discriminator such that the sampling from the foreground times this segmentation mask plus the sampling of the background times the background. This is not an empty region. So as we can get a meaningful segment network. And we test our method on a flower data set that contains over 6,000 training image and over 1,000 test image. After training, we see that the inference speed is around 0.02 seconds for each image. It's very fast. And also we can see that we reported the training accuracy, the training mean IOU, test accuracy, and test mean IOU. And we will see that our method does increase the accuracy of the CV model by a large margin. Also, compared to the recently proposed the redo method, our method is still better. This here are the visual results. The first column is the input image, and the second column is the ground truth. This is the ground truth labeling by human. And the third column is our inference, the mask. And these last three columns are our latent information. This is the mean of the encoding image, and this is a variance, and this is a reconstructed image. And we will see that actually in the latent space, the segmentation mask and the mean image are very, very similar. Okay. In the next, we turn to a more general case in which that we have given two sets. One set is a clean image, xi, and the other set is noise image, yj. But this xi and yj are not paired. In this case, if I want to learn a deep network, there are three procedures. The first step is we try to learn a degradation model between the clean image and noise image. And using this degradation model, we can construct a synthetic training data set. And use this synthetic training data set, we can learn the deep neural network. So in this procedure, we will see that the most important part is the step one, which we call the step one as the unpaired degradation modeling. So this is actually fit for this super resolution task, which means that in real applications in super resolution, we assume that this block kernel K and N noise are both unknown. So the traditional method use interpolation to substitute to replace this block kernel, but this is inaccurate. So we try to get a better degradation model for this task. In fact, this unpaired degradation modeling is an inverse problem, which means that given two distributions, Px and Py, our goal is to recover the conditional distribution Py conditional on x. In general, this problem is difficult because we know Px is known. Recovering this conditional distribution is equivalent to recover this joint distribution. However, Px and Py are the marginal distribution of this joint distribution. So the number of observations here is insufficient. So this is not a well-posed inverse problem. To handle this case, we need to do some independence assumption, or we can use some regularization will be helpful in this case. In our method, we adopt these independence assumptions. This is very straightforward because if the Px and y are independent, then the joint distribution of Px and y is equal to Px times Py. And in this case, the log likelihood can be decomposed as the log likelihood of Px and the log of Py. But in image processing, we know that x and y are correlated because x are clean image, y are noise image. So they are correlated, which means that this identity does not hold. In our method, instead of directly consider this independence, we consider a conditional independence by designing this generative graph. This generative graph means that the clean image is only correlated with Z, and the noise image is correlated with Z and Zn, which means that the Zn is the noise here. Once we have this generative graph, and we can show that this conditional likelihood can be decomposed as the summation of these two terms. And in these two terms, it does not require the pairing information between clean image and noise image. So which means that I get a decomposed likelihood. So now let's formulate our model. So we consider one is a generative model and one is the inference model by using our generative graph. And similarly, we can estimate the likelihood using a similar method, like we call this is able. This is a lower bound of this log likelihood. And in this equation too, we find that it still needs a paired information because this conditional distribution, Z conditional on both clean image and noise image. So to get this distribution, we still need the paired data, and we cannot decompose this log likelihood. And in our model, we further assume this inference invariant condition, which means that for any sampled paired image, we assume that its latent information should be the same. So it's very natural because for clean image and the noise image, we assume that the latent information should be same. Once we have this inference invariant conditions, then we can decompose this able term as a summation of able x plus able y. This able x is only related to the samples of P of x, which means that it does not correlate with y. It only related to the clean image. And this able of y is only related to the noise image. So in this case, this new able is our minimization loss. So this condition is very critical in our method. We give some more explanations of this condition since it is very important. We assume the simplest case is in the Gaussian corruption case, which means that y is equal to x plus n, but n is a Gaussian distribution. We can define some pre-processing operator, which adds some Gaussian noise to the clean image, or add another Gaussian image to the noise image. So we know that this hx is equal to the Gaussian perturbation of x, and y is also another Gaussian perturbation of x. So the conditional probability of z conditional on hx and the qz conditional on hy should have this form. So the distance of these two distributions probability lies on the distance of this pnx and the pny tilde, right? And we can see that if I let this noise level goes to infinity at the same speed, we will know that this the KL divergence of these two distributions will goes to 0. Here, the big K is the dimension of the latent space. So it's a constant. So which means that this distribution goes, the distance of these two distributions goes to 0, which means that our inference invariant condition holds asymptotically. So we can use some preprocess operator to assume this inference invariant condition. So in our implementations, we actually use some preprocess for the low resolution image and high resolution image, like the HY and HX. And then we go through a 3-layer VAE architecture. This is different from our previous work. Here we use a hierarchical VAE structure. This is inspired by the hierarchical VAE's paper. And also in the construction of our latent image, PZ and PZN, we assume PZ is in the discrete space and PZN is in the continuous space. This is for the better reconstruction. This is also an assumption in VQ-VAE's method to achieve high resolution image. So this is our network architectures. And in this figure, we will see that this is a clean image, and this is a noise image. This is a real low resolution noise image. And this is a synthetic noise image by our method. We call it as a log VAE's method. And the last column is our noise distribution. We can see that it's almost close to the true noise distributions here. And in our experiments, we test our method in 2 super resolution challenges. And each challenge contains 100 color image, and each image is around 2K. We compare our method with 5 methods. The first method is bicubic, which means that usually we can directly use bicubic interpolation to construct our synthetic data set. And FSLR is a winner of AIM 2019, and Impression is a winner of the other challenge. And the DASR and DFlow are GAN-based approach and flow-based approach respectively. Both are proposed recently. And this is the result. We reported the PSNR and SSRM and the LIPS. LIPS is a perception score of the feature in the challenge. So in these 2 data sets, we will see that the proposed log VAE achieves very competitive performance. And this is an example. And we can show that this is a zoom-in version in our super resolution results. And here, this log VAE is our method. We can see that it is very clear in the in this high resolution image. And this is the other example. And we can see that the leaves of here is more clearly than all the other methods. Okay, now let's summarize my talk. So in this talk, I think I want to propose that modeling error in many applications, it should be important if we want to recover this high quality image. And we should to handle these errors carefully. And the deep neural network are helpful in this case for describing this error if we do not know the exact physical principles of this error. And we have shown this case in the unpaired data regime, consider the single image case and data set case. And I want to emphasize that a feature of our networks proposed in this talk do not need any pre-training networks. So I think this is an advantage. And after all, I want to give a take-home message is that in the unpaired data regime, actually we can build up connections between the classical model and deep neural networks by using the variational inference framework, such that we can integrate both methods and to achieve a better results and some more explainable architectures. Thanks for your attention. That's all of my talk. And here, this is a reference of this talk. And thanks for my collaborators and my students, Zhendi Han, who implemented all these methods and in this data set. Okay, thank you.
Thank you, Chenglong. So, so now is the Q&A time. So, if you have any question, please either you put your question in the chat box or you raise hand, and then I can allow you to speak your question directly. Please. Okay. Meantime, maybe I start the question first. So in your the segmentation model, because you say that the CV, the classical model, the objective is not strong enough to learn the mask, the segmentation mask. So you say that you add the additional regularization into the objective. That is allowed the rotation invariant or the other. I'm not so sure exactly what you this is somehow the, what do you mean? This is a regularization term. So you mean you will add this directly in your network to learn this U, correct? On your mask or segmentation mask. This U is the network, correct?
Yes.
Okay, so that means that you add this additional regularization like the rotation invariance or augmentation invariance directly into objective in the network. Oh, okay. I see.
Yes.
Okay, and in particular, you propose two. One is the region information, and another is, so which one will be better, or in your numerical result, which one you use, or you use both together?
Yes, in our model, we actually use both together, we have reported the application studies of these two regularization terms, and I think the first regularization is to increase the variance of these training samples, and the second term is to avoid our model reduced to some trivial solution or some bad local minimum.
Any question from the floor? Or? Yeah, Jennifer, do you have any question?
No, I'm fine, thank you. There's a lot of background noise going on here in my home right now, so I'm staying muted.
Oh.
It's morning here. Everyone's leaving the house for school and stuff like that. Coffee grinding.
Okay, that's all right.
Sorry, yeah.
Okay.
Yeah, maybe I ask one more, I think, and then to see any other question from the floor. So Chenglong, in your first formulation to using elbow, the lower bound, in your objective, you have the expectation of the epsilon. I forget, maybe in the slide number 16.
Okay, I think. Is it?
Maybe,
is it?
Maybe next slide, next 16.
Yeah.
Yes, here in the elbow is, and then you have an objective, your expectation of epsilon. Here, you have epsilon. Yes. So what does it mean? Your expectation of epsilon here is what does it refer? I just because in your latent space assumption, encoder and decoder assumption, you don't have epsilon. So I just want to clarify. What does it mean?
Yes.
Yeah.
This epsilon that comes from the expectation, that comes from this expectation term, like the elbow of this first term. And in the first term, we need to compute an expectation. And here, this expectation is with respect to some Gaussian distribution. And we use some reparameterization trick, and we can reduce it as by using some scaling or something. We can reduce it to a unit Gaussian distribution. Okay, in this in the estimation of this expectation. And in variational autoencoder, this is also called as a reparameterization trick.
Oh, okay, I see.
And in each step, we need to resample this epsilon to estimate this objective function.
Okay, because you need to calculate expectation. Yes. So, okay.
Yes.
That's nice. Okay. So, any questions from the floor? Yeah, you can put your question in the chat box or you raise hand. Yeah, that's very nice result. I think that's very interesting. You using unpaired data or even the enabled data. To do in the network, and you also categorize how to add relational model directly to the network model.
Thanks a lot.
So I think if we do not have any question, I think in case if you have question, I think you can use send an email directly to Professor Bao Chenglong. I think not difficult to find his email address from his Tsinghua University website, or you type in Google or whatever, the Professor Bao Chenglong, you can find his email. So definitely he will be happy to answer any question. Yeah, definitely I will have more questions after. Maybe I read more, because there will be a lot of interesting results. So maybe okay. So if you do not have any question, maybe let's thank Professor Bao Chenglong again for his very exciting talk. And yeah, okay, good.